The last time, I gave the following definition. I said A and B are related if they have the same size. And my definition here was there exists a bijection. Because this is the way we're starting to count things, right? This is the way that we want to count sets in general. It may seem silly for finite sets, but we need to develop this to get to a more general notion. Last time, this is an equivalence relation. And notice, this is cleared up by the fact that this is a bijection, right? I don't have to talk about infinite size sets here. The notion here, this is going to mean that there's a bijection from the set A to the set B. The equivalence relation means, of course, bijection from A to A that is reflexive, symmetric, because if there's a bijection from A to B, then the inverse is bijection from B to A. And transitivity from if A and B, if there's a bijection from A to B and a bijection from B to C, the composition is a bijection from A to C. So here is a theorem. A, B, C, D sets with and let's say that A and B have the same cardinality and B and C have the same cardinality. Then number one, A and C are the same size and B and D are the same size, using that terminology loosely. Then A cross B and C cross D are the same size. And two, if A and B if A and B are disjoint, right, nothing in common, and C and D are disjoint, again, their intersection is empty, then the cardinality of cardinality of C. Okay, so let's prove this. That might be useful. I'll leave the proof one for an exercise in notes, but I want to do it here. It's worthwhile. How would we go about number one? Number one, I need to show that these two are the same size. So I need to find a bijection from A cross B to C cross D, right? First, let me tell you the tools that I have. What tools do I have? I know that these two animals are the same size, and so are these. So there exists bijections. I'll call them F and G. Well, there exist bijections A to C and G from B to D. So what do I need to do to establish this? I need to build capital F from A cross B to C cross. Well, let's do it. What does an input of this look like? Well, it's an order of pair. It's this. F of A, B. Now, I need this to give me an output in C cross D. Maybe using some tools I already have. And remember, even though it's 8 o'clock in the morning, it's math class. So we don't do anything unless it's easy. What's the easiest way that I can get C, given all this data here? Okay, use the bijection. F of little a. And same kind of thing here. G a little bit. This is the way my function works. It's sort of like a product of the functions, right? Little f on the first coordinate, little g on the second. What do we have to prove about this? We need to prove this bijection, right? Okay. All right, now, this function. Because any output AB gives a unique output here because f and g are both functions, right? Show, well, because f and g are let's prove that f is 1 to 1. So suppose that f of A1, B1 is equal to f of A2, B2. What does this mean? This means that little f, A1, little g, B1, that ordered pair is little f, A2, little g, B2. Right. Now, what does it mean for these two things to be the same thing in C cross D? It means their coordinates must match, right? That's what equality means in a product. So we have f of A1 equals f of A2, and we have g of B1 equals g of B2. But what do we know about the functions f and g? They're bijections, and what's relevant here is the fact that they are 1 to 1. Good. We are 1 to 1. So A1 equals A2 and B1 equals B2. And so A1 B1 is equal to A2 B2 and F is 1 to 1. I agree with it. Okay, we got that way. What about onto? Let's pick some. What do we have to do to show it's onto? We have to show that anything in the codomain can be reached by something in the domain, right? So let's start off here. Well, how are we going to find something that goes to it? Where does C live? C lives here. And what do I know about F? It's a bijection, and in this case in particular, it's onto, right? Since F from A to C is onto, there exists A in A such that F of A is equal to C. And you get the same thing going on with the other one, since G from B to D is onto, there exists B and B such that G of B is equal to D. So here is kind of a climax of this. So if you look at capital F AB, this is little f G, which is CD. And so I've shown this one and onto. F is the bijection, and this shows the target. Okay, key questions. I want to show this. I am going to not do, I've got two in your notes. I'm going to go through part of two, polish up something, and then I'll let you finish it off. I've sketched two. So I want to think about the way this function is going to work. So here's what we have in two. A intersect B is empty, and C intersects D is empty. So that's the assumption here. We also have the blanket assumption that A and C, B and D. So also F from A to C, G from D to D are bijections. So what we now, okay, so before we had to define a function whose domain was A cross B. Now we need to find this time from A union B. Um, hmm. How are we going to do this? Right. So how do we get the function?
Because since they're destroyed, they're going to be sectors. And then since we know those are equal, we have cardinality.
What if one of the sets is infinite? I mean, that's that to me that throws like a little bit of a monkey wrench into it.
And we have an X A union B, which is equal to
A plus B for some A, like little A plus little B for
The
some.
problem is these are abstract sets. I don't even know if I can add things out. Right? That's what the problem is.
Like X, we let me know that or anymore.
So you look at X, right? X is. Right, because that's the domain function that we're trying to build. And you say, hey, you're either in A or B, right? What happens if you look at X and it's in A? Well, let's use that. What if it's in B? Use the other. Now, here's the problems. What if it's in both? It can't be, and that's what allows us to make this point. This is a well-defined function. Has A intersect B is empty. That is to say, no X is in both. So any input gives one and one, only one output. Right, that's crucial here, right? I think onto is probably fairly simple. Why is that onto? Well, let Z be in C U D. And Z's in one of them, right? If Z is in C, then there exists A in A such that F of A equals C. And if C is in D, then there exists B in B such that G of B equals C. So, let X equal A if C is in C, and X equal B if C is in D. And note, capital F of X equals C. So F is on. Notice, I did not use the fact that C and D are disjoint. It's not necessary as part of the first, but I bet you it's gonna be necessary for the one-to-oneness. Why is this? Well, let's suppose. Well, suppose. Let's. Your X and Y are in A. U. Case one, X is in A. This means that F of X is, if I use my rule here, since X is an A, it's gotta be a little f of X, right? Which is in C. Correct? But. But f of X and f of Y are in the same place. Right? And C intersect D is empty. Which means if f of Y is in C, then this means that Y must be an A as well. Right? Because it can't use this rule because this output is in D. And f of Y, since it's in C, it can't be in D. Therefore, f of X equals f of Y and C. And so X, Y. Everybody okay with it? Here in this last step, we of course use like the lowercase f is 1 to 1. And case 2 is almost the same. X is in D, so f of X is, in this case, g of X, which is in D, we go for the same. Part. Okay, any questions on
About, this is kind of getting into the final conclusion. So like, the fact that, like, G is from E to D. So like, if we're just looking at like the order that's equal, how can we say that like G from E to D is onto, is it just the fact that we stated that it's by?
That's by definition. That's
Okay.
right. Because when you say B is equal to D, that means there is some bijection from B to D. Right?
Okay.
There's some one-to-one and onto function from B to D, and I call that function for the purposes of our proof achievement. Okay, so here is a definition. It might seem a little silly, but we're going to do it anyway. So that's how we roll. Definition 515. Actually, maybe not so silly. So let me ask you a question. Just for me before we start. Somebody tell me what a finite set is. Give me a definition of finite set without using the word finite. But with natural numbers infinite. Right.
You can just, the cardinality of the second, and then you get the natural first, that's less.
Okay. Okay. Right, so let's do that. I mean, both of these ideas actually have a lot of merit. But it is, I mean, it's not clear at first, right? It's kind of hard to use finite thing. Let's say a set. I'm gonna call it something. S is finite. Yeah. S is empty, or if the cardinality of S is the cardinality. And I'm introducing a notation here. Uh, and I apologize for this a little bit, but when I have this capital N sub zero, that means the natural number is zero thrown in. When K is bigger than one, I mean the cardinality of this finite set that has exactly the numbers 1, 2, all the way up to K. Right. So in other words, if S is empty, then we say cardinality of S is zero. If we say cardinality of S cardinality means the number of elements in it. It also means, more formally here, what it means for a finite set is there is a bijection from the set. So for example, here's a concrete example. Square. There you go. Base Cheerio. Okay, here's a set of like, how many things? 5 things, right? The cardinality of S is, there's 5 things in it. And this is the cardinality of set 1, 2, 3, 4, 5. Because there is a bijection. 1-to-1 correspondence between now, this is like really, I know it seems heavy-handed compared to saying, there's 5 things there, right? But thinking about it in these terms here is going to be useful to us in a much larger context. So here's kind of the first observation, which I will leave as an exercise for you. There's not much to it. There's no surprises in this whole theorem here. Proposition. Here, A is final, and cardinality of A and B are the same. That is, A and B can be put into 1-to-1 correspondence, then B is final. There's a bijection. This is the statement today is like today is finally said. There's a bijection from let's see. If A is not empty, and there's a bijection from A and K. And a statement right here, there's a bijection from A to B. Everybody agree with that? So notice that if you do, do G inverse and then F, this is because the inverses and compositions bijections. So now we get a bijection, which is exactly what it means for B to be finite. Right. So that's being technically correct. What happens if it's empty? Well, if A is the empty set, the cardinality of A and B are the same, by definition, then B is also empty, and of course it's also finite. I bet, yes. This one. Suppose that S is a finite set. Yes, it's finite. Cardinality A. So that means either it's empty, if K is 0, or it can be put into bijective correspondence with, set NK. And suppose X is not in S, so since it's not already there, then the cardinality of S union X. Anybody want to guess? Okay. Proof. If S is the empty set, then S union X is equal to X. And the cardinality of X is clearly one. One thing in there. If S is not empty, then there exists a bijection. We'll say F from S to NK. Now what we need to do is see what happens with S union X. One with S union X to NK plus 1. Which is NK union. How does this bijection work? Well, F1, let me call it C, is equal to F of C if C is in S and K plus 1 if C equals X. So you just build, this is kind of an inductive type argument. And this is also very similar to what we did earlier with the union. So you do the same read thing, right? Take your input. It's either X or it's in S. If it's in S, just do what the previous bijection did. If it's X, take it to the new guy, right? That's it. Okay. Any questions? I'm gonna use this stair step to prove a slightly more general theorem. Every every subset of MK is fine. So we're gonna prove this deductively. Nice chance to practice on induction. We're gonna proceed by induction on K. Let's look first in N1. The only subsets are the empty set, which is actually the whole set. So all subsets are finite. Now I'm gonna impose an inductive hypothesis. Suppose that all subsets of NM are finite. Inductive hypothesis. Suppose for some M written by one, all subsets now, all we gotta do is consider. So our inductive hypothesis is suppose that NM, some n greater than or one, NM, all subsets are finite. Now let's look at let's consider n plus one. Now suppose, well, consider now, let S be a subset. Note that look at S, right? Take your subset, take out n plus one. And don't worry, even if S didn't have n plus one in the first place, you're not doing anything, right? So remove n plus one if it's there. And if it's not there, just don't do anything. Notice that when you take S and you remove n plus one, then that is a set of, that by induction is, because now this is a subset of NM, right? Because it doesn't have n plus one in it, it's a subset of NM, and it's finite by the inductive hypothesis. Yes, still parts of the integers in the finite set, so no, it doesn't apply to all integers. So suppose that S minus n plus one is equal to S. Then all subsets of S are finite by the previous state. So in other words, what this says really is if n plus one wasn't an S in the first place, then we're done. All subsets are finite. And the only thing you have to worry about is if n plus one was actually in S in the first place. So how do we tackle that? Well, if not, then S minus n plus one U n plus one is finite by the previous. Well, let me point out, this is equal to S. So by deduction, n sub k is always finite. Sorry, all subsets of n k plus one are finite. Okay. I will leave this for an exercise because it's really just an adjustment. So the follow up on this is theorem. In this case, what we have 5.9. All subsets of a finite set are finite. So I'll leave that as an exercise. Let me point out, this may seem like really kind of pedestrian, if you will, and I'll admit it kind of is. But let me point out, there's a couple of subtle things. First of all, if you have an infinite set, this is certainly not true, right? It's not true that all subsets of an infinite set are integers, right? There's certain finite subsets of the integers. I just take an integer. Here's another thing that we're going to find out that's kind of weird about, and this is by counting finite subsets, right? So would everybody agree that the set of people on this side of the room is a smaller set than the set of people on this side of the room, right? And the set of all the people in the room is the union of these two sets, right? Now, you all are a subset of everybody in the room. are you the same size as the set of all people in the room? No, because we'd be missing these two, right? This is another kind of confounding thing about counting in sets. You can take infinite sets and throw out finite sets, and they're still infinite. Right? So if there are infinitely many people in the room, we could lose you two, right? You know, no offense, but there would still be infinitely many people in the room, right? In fact, if you do it carefully, you can take an infinite set and remove an infinite set and leave 23 elements. You could take an infinite set and remove an infinite set and leave no elements. You could take an infinite set and remove an infinite set and leave an infinite set, right? And this is very different than what happens for finite sets. Very different. Okay. Let us continue here. Let's let A A1, A2, A3, and P sets. If A and B are disjoint, that is A and B are disjoint, then A union B is equal to um, yeah, I think that I'll add speak finite sets here. Oh no, I'm gonna. Yeah, I guess so. This is true in general, although I'm only going to discuss the finite case for now. But if you have two disjoint sets, then now the question that might come to your mind is what do I mean by adding infinity, right? Just think about this in terms of finite sets for now. We'll deal with the other more mysterious one later. In general, if A and B are finite, then like this, and 3 union, if each AI is finite, and so is union. In one in. So the union of a bunch of finite sets, well, let me restate, a finite number of finite sets is finite. So, right, I think that this is probably a good place to stop. Pick up the proof of this next time. Any questions? Questions? All right. Friday is Pi Day. It's the last day before spring break. Neil Calkin will be talking to us about things that are not Pi. Because Pi should be very interesting. Neil, great school. Good ones of this. mathematical kind of trickery and recreation. I encourage you to be there, and I